Okay, so today we're working on limits at infinity. We did limits to infinity the last time because a lot of these things, right, there were asymptotes. There were vertical asymptotes. Let me look at the notes from last time. There were things with vertical asymptotes that we couldn't cross, right? So the function either went down to negative infinity or up to positive infinity. Today, the difference is we're looking at where x approaches infinity or negative infinity. So where the function starts and where the function ends. In other words, end behavior. End behavior. So what is end behavior? End behavior is at the end. Well, where is the end of a function? Positive infinity or negative infinity, right? How is it behaving? What is it doing? That's another word. That's another way of saying what we're doing today. Okay, so I have a function here. All three are the same. 3x squared over x squared plus 1. I did two tables and the actual graph, just to give you a visual of what we're doing. Okay? So we need to find the limit as x approaches infinity. Well, what's always our first step when we're trying to do a limit problem? What's always the first thing we should try when we're trying to do a limit problem? Even before that, plug in the number, right? Plug in the number. What's the problem with plugging in a number? Yeah, we can't plug in infinity. Infinity is an idea. I can't put in infinity to my calculator, right? It's an idea, right? So we can't really do that. So we got to think of another way. So that's what we're going to do today. So the first table is x approaches infinity. What do you notice about the x values on my table? They're getting bigger, right? They're getting bigger. They start at 1, then they go to 100, then they go to 1,000, 10,000, 100,000, a million. I stopped there, but so in other words, as x is approaching positive infinity, what is y approaching? 3, right? 3. So we would say the limit as x approaches infinity is 3, because as I plug in bigger and bigger numbers for x, it's getting closer and closer to 3. Actually, it's not. One of the things I don't like about Desmos is that it's actually not 3. These are 2.999999. But if they run out of space, they eventually just round up. So actually, these 3s should be kind of look like this guy here. 2.999999999. But eventually there was too many 9s, so they just rounded up. So it's not actually 3, but it's close to 3. Very, very close to 3. Okay, so let's look at the other side. What do you notice about the x values as I go down here? They're getting bigger in the negative direction. In other words, they're getting smaller, right? They're getting smaller. They're going on the number line. See, I got a number line somewhere over here. On the number line, they're going this way. That's the negative direction, negative infinity, right? So, what y value are they approaching? They're approaching 3 as well, right? So we would say this is 3. This is the same, the graph here is the same function as these two. This is the same as this, as the same as this. They're all three the same. One is just as x approaches infinity, as x approaches negative infinity, and here's the picture, what it looks like. So what are things that you notice about this guy? Anything that stands out. What are things that stand out for this guy? For this, it's purple on mine, but what do you notice? It looks like it. So it goes, and then it kind of does this little parabola thing, and then dips up, and then goes like that, right? It flattens out a little bit. where does it flatten out at? At where y equals 3, right? Where y equals 3. In other words, there's kind of an invisible line here at y equals 3 that it's never going to cross. We've seen those invisible lines before, right? They're called asymptotes. The difference with this one is that it's not vertical. It's a horizontal asymptote. Okay? It's a horizontal asymptote. It's a horizontal line where the graph will never meet. Even though it says 3 here, these aren't actually 3. They're 2.999999999. Okay? That's what we're focused on today. That's what we're focused on today. So because we can't plug in infinity, we have to have other ways, right? If this was as x is approaching 3, as x is approaching -3, go for it. Plug it in, see what you get. But you can't plug in infinity if we don't know what infinity is or looks like, right? So that's why we're doing this. Okay? So this is what a horizontal asymptote does. Horizontal asymptotes, often you will be asked to take the limit of a function as it approaches infinity, right? Just like we were earlier. When taking the limit at infinity of a fraction, rational function just means a fraction function, where p of x and q of x are polynomials, multiple terms. If the degree of p is greater than the degree of q, there's a word there we haven't seen this year in this class. What does degree mean in math? I know degrees means like Fahrenheit, Celsius, but not in math. That's in science. What does degree mean in math? Angle. Not the angle. Largest exponent. Largest exponent. Right? So for example, this guy right here, this limit here. What is the degree on top? 2. That's the largest exponent. What's the degree on bottom? 2. So we would say they're equally balanced because the degrees are the same, right? That's what I mean. That's what a degree is. Okay? So when the top degree is bigger than the bottom degree, our answer is always going to either be positive or negative infinity. Positive or negative infinity, depending on signs. Okay? So if the degree is higher on bottom, your answer will always be either positive or negative infinity. One of those two. Okay? What if they're equal, like the first one? What if they're equal? Then the limit is the leading coefficient of p divided by the leading coefficient of q. Okay, so let's break that down a little bit. What does leading mean? If I say leading, front, right? In front, first term. What is coefficient? There you go. So let's go back up here and look. On top, what is the leading coefficient? 3. Not the x squared, that's the variable. On bottom, what's the leading coefficient? 1. The one in front of here, right? Not this one here. Okay? So it's saying if your degrees are equally balanced, like they are here, the answer is a fraction of the leading coefficients. Well, what is the leading coefficient on top, you said? 3 divided by equals. That's how we got the answer. Okay? All right. We call those equally balanced. Equally balanced because the degree on top isn't bigger than they're the same. What about bottom heavy? What about if the degree on top is smaller than the degree on bottom? The answer is always 0. Answer is always 0. The limit's always going to be 0. Okay? That's in words. So if you look on the back of this page, I put a little table. I did a little table here with some examples. We're going to do the same thing. We're going to do the same thing, except we're going to write it in a table form. Okay? We're going to do the same thing. So on front is words. Sometimes it makes sense to people. It sounds like it makes sense to you guys, but I also do a table because tables are more visual. Okay, so the degree. So what if the degree of the numerator? Numerator is the top, right? What if the degree of the numerator is the top? So the answer is always going to be positive or, top heavy. So in other words, top heavy is the first one, right? Yeah. Top heavy. So the limit will always equal positive or negative infinity. So let's write that down. Because the limit is positive or negative infinity, it means it's either going to go up forever and ever and ever or down for ever and ever and ever. There's going to be no horizontal asymptote. No horizontal asymptote, if that's the case. Okay? Because the limit is either going to go up forever and ever or down forever and ever. Can't cap it. A horizontal asymptote caps it. Can't go above this line. Can't go below this line, right? So let me give you an example. Let's try an example. F of x is equal to, let's say, x to the third plus 2x over 2x squared minus 5. What is the degree on top? 3. What is the degree on bottom?
2.
The top is larger, right? So therefore, we would say horizontal asymptote equals none, because there is none. There is no horizontal asymptote. And if they ask me the limit at f of x, what would that be? Either positive infinity or negative infinity, right? Which one is it? We'll talk about that later. Okay. Let's look at the second one. The degree in the denominator is larger, bottom heavy, right? What's the limit? So this one is top heavy. What's the limit going to be here? The limit will always be 0, right? So if the limit is 0, guess what the horizontal asymptote will always be? 0. So because horizontal asymptote is a horizontal line, we write it as y equals 0. Vertical asymptote, x equals. Horizontal asymptote, y equals. Okay. Let me give you an example. Two x squared minus 5 over x cubed plus 2x. What is the degree on top? 2. What is the degree on bottom? 3. Top heavy or bottom heavy? Bottom heavy. So if it's bottom heavy, we say the limit is 0. And where is the horizontal asymptote going to be? Y equals 0. Yeah. Thanks. Okay. Degrees are the same. Degrees are the same. So in other words, equally distributed. Equally distributed. If they're equally distributed, what is the limit going to be? Leading coefficient of the top divided by the leading coefficient of the bottom. Just like we saw in the example earlier, right? So, let's see. So let's write this down. Fraction of leading coefficients. Fraction of leading coefficients. Okay. Top heavy, bottom heavy, equally distributed. So let me give you an example.
Is this only when x is approaching infinity?
Yes. We only use these when either they ask us one of two things. They say x is approaching positive infinity or negative infinity, or they ask us for horizontal asymptotes. This is the only time we use this table. Good question. Yeah. If they say x is approaching -2, then you do what we've done in the past. Don't do any of this stuff. Okay. Okay, so let me give you an example. Three minus 1x squared, or sorry, not 1x squared. 3 minus x squared over 5x squared plus 2x. What's the degree on top? 2, right? It's 2. Degree on bottom, 2. Equally distributed, so we're going to use this one. What is the leading coefficient? Be careful here. What is the leading coefficient on top? -1, right? -1. I know you see that 3 in front, and you're like, oh, 3. No, but that's not the leading coefficient because it goes with the degree. So -1, good. And then what's the leading coefficient on bottom? 5. So a fraction of that would be -1/5. So the limit would be -1/5, and the horizontal asymptote would also be at -1/5. Okay. Okay. So now what we're going to do is I'm going to ask you two different questions. I'm going to say, what is the limit as x approaches positive infinity or negative infinity? And I will also ask you, what is the horizontal asymptote? I'm essentially asking you the same question, just different ways. Okay? Okay, so let's look at it. 1a. Let's finally get to an example here. So this is a binomial, right? 5 minus 2x squared. So one of the properties we can use, one of the things we can do is break them up. So what I'm going to do is I'm going to break this up because essentially I'm trying to find the limit as x approaches infinity for both. Okay? So what I'm going to do here is I'm going to say the limit as x approaches infinity, first for 5, minus. And then I'm going to say the limit as x approaches infinity for the second part, 2 over x squared. We haven't talked about the properties. We'll talk about it probably later this week. But that's one of them. You can break it up into pieces. Okay, so let's look at the first one. The first question, first part of it first. I'm going to highlight that in yellow. What is the limit as x approaches infinity for 5? It's just going to be 5. There's nowhere to plug in anything. It's always 5, right? It's always 5. So there's nowhere, I can't even plug in anything. X equals 5 is just going to be like this. Where is it approaching? It's always 5. Okay? So this guy is just 5. Minus. Now let's do the second part. This one's got a variable. But again, I can't plug in infinity because it's not a number. But does it look like one of these guys up here? Which one does it look like? Is it top heavy, bottom heavy, or equally distributed? Bottom heavy, right? The bottom has a degree of 2. What does the top have? A degree of 0. So it's bottom heavy, yeah. What do the rules say for bottom heavy? As x approaches infinity, what's the limit going to be? 0. So this whole guy is equal to 0. And 5 minus 0 is just 5. Because this guy, if there's no variable, it's a constant. It's always going to be 5. If it was 5x, that's something different. But because it's just 5, it's a constant. It's always just going to stay that way. Yeah. Mm-hmm.
Fraction on right became 0.
Because it's bottom heavy, right? The degree on bottom is bigger than the degree on top. So according to our table, when the degree on bottom is bigger, it's bottom heavy. So the limit's always going to be 0. The vertical or horizontal asymptote's always going to be 0 too. Okay. B, I kind of change it up on you a little bit. But it's not as bad as you think. It's got a fraction. But what's missing about it or what's different about it? Yeah, if I said, what's the degree on top? What would you say? 0. I agree. What's the degree on bottom? We don't know, right? We don't know. We don't know because it's not a polynomial. It's what we call exponential. Exponential. Well, here's the thing. Here's the thing I'm going to let you in on. And that goes to this that we kind of skipped earlier, this part here, the growth rate. These are the things that grow fastest. Fastest. This will help us determine if it's top heavy, bottom heavy, or equally distributed. So what we've been working on are polynomials. Polynomials are things like binomials, trinomials, 4 terms, monomials, right? That's polynomials. The only 2 things that grow faster than polynomials in this class, well, there's 2 things, factorials and exponentials. Factorials you don't have to deal with in this class. Factorials we don't deal with in this class. So you don't have to deal with those. Those are, I don't know if you've ever seen those. It's the, if you see a number with an exclamation point behind it. So like 5 exclamation point. Exactly. It's 5 times the next biggest integer times the next biggest integer times the next all the way to 1. Right? So those things grow fast, extremely fast because you're multiplying, right? We don't have to deal with those in this class. The biggest thing we have in this class are exponentials. They grow fastest. Exponentials. Those are the things that when you graph, they start slow, but then they shoot up like that. All right? Then polynomials. Then logs. Then sine and cosine. Sine and cosine they're kind of oscillate. Because sine and cosine just does this. Goes up, goes down, goes up, goes down. It doesn't go up and doesn't go down too much. Constants never grow. 5 was a constant. That's just going to stay 5. It doesn't grow. Okay? So let's go down here. The top, 3 is a constant. Is that going to grow? No, it's going to stay 3. Bottom is an exponential. How do I know it's exponential? Not because it has e, because not all exponents have e's. Because where's the x? Exponent. When the exponent is a variable, you got exponential. So a lot of people see this. Oops, no, not that. A lot of people see something like this, and they're like, oh, that's an exponential. No, because the exponent needs to be. If I want it to be exponential, I would do this. That's exponential. Okay, so since the bottom is exponential and the top is a constant, do you think it's going to be top heavy, bottom heavy, or equally distributed? Bottom heavy, big time bottom heavy. This guy is big time bottom heavy because of the exponential being on the bottom. So what are our rules for what's the limit as x approaches infinity? 0. In other words, if I kept plugging in bigger and bigger and bigger and bigger numbers, let's say I kept plugging in bigger and bigger numbers for x, right, until I get to infinity. What's the top going to do? Stay the same. It's never going to get bigger, right? Bottom is going to be doing what? Way bigger. It's going to be getting way big. So the top's going to, as I plug in numbers that are closer and closer to positive infinity, the bottom's getting way bigger. Top's just staying 3. Eventually, that's pretty much 0. If I plug in a number big enough, it's going to be 0. Okay. All right. Okay. So let's see. Let me look at letter C real quick. Let's do letter C and then we'll be done for today. Let's do letter C. We'll be done for today. I can finish this in a few minutes. Top. Top is a trig. Bottom. What is the bottom? Bottom fits into which of those categories? Which of those categories? I know where the top is. It's right here, sine and cosine, right? Where does the top fit in? The bottom. Not a constant. Constant's just a number. It's a polynomial. If it's a variable, if it has a variable, it's at least going to be a polynomial. So which one's going to grow faster, the top or the bottom? Polynomial, right? Growth rate. So the sine and cosine don't grow very fast because they just oscillate. They just keep going back and forth, back and forth, back and forth. Just if you don't believe me, look at sine and cosine. What's the biggest number you have on there? +1. What's the smallest number you have on there? -1. They can't get any bigger or any smaller than +1 or -1. That's as big as they can get. So that's not growing very fast, right? The bottom is a polynomial, right? The bottom is a polynomial. So that one's going to grow faster. So we would say this equals 0 because it's bottom heavy. Okay? That's essentially what we're doing. The only new thing we're going to throw in is the next one. I'm going to throw in a negative infinity. That's going to a little bit, not too much. Okay? We'll do that tomorrow. We'll talk about that tomorrow. All right? So we'll finish this and go from there. So no new homework. The only homework you have is the one I assigned yesterday. So if you haven't finished that, it's not due till tomorrow. But yeah,